In the previous couple of videos, we've been learning how to find maximum or minimum of a three-dimensional and later on n+1 dimensional function. So look, now we're gonna go back to functions with just two variables. So we will have some z equals f of x, y, but we will try also to find maximum or minimum of this function. But this time we're going to introduce a constraint. What is this constraint? Look, there is usually we don't have the luxury of choosing any value of x and y in the process of finding maximum, especially in economic, financial or management problems. We can only choose from some values of x and y. So now I'm going to introduce something we're going to call a constraint. And I'm going to first introduce it in a general form. So let's just say that we've got g x y equals to some c, where c is a constant. Okay, look, so how does our problem works right now? Look, we are still dealing with function of three dimensions. Z is a function of x and y. So basically, we are going to draw this function in a three-dimensional space. But now we've got this additional information that we no longer can choose any value of x and y, but we can only choose those who are fulfilling our constraint. Look, how this constraint will look like. I'm going to actually start today with more complex case. We're going to see how we will find maximum or minimum in a more complex case. And then we will go back to the easier case. But look, let's start with how would it work. Look, imagine again that we are looking at our three-dimensional coordinate space from above. So look, here we have some y-axis, here we have some x-axis. And look, imagine that we are looking for maximum. And let's just say we already know that this maximum is located over here. So here we have some spheric shape, and let's just say that this is the top of the spheric shape. Now, I hope you remember that that when we were doing this, using optimization techniques we introduced before, all we had to do is to find a point at which both tx, so derivative with respect to x, and ty are tangent to this point and have zero slope, right? This is basically how we were getting this. Then we were using second order condition that, assuming that this is maximum, was saying that doesn't matter in which direction we are moving from this point, we are always getting lower. Because if this is a top, then doesn't matter where you move, you're getting lower. Okay, so knowing this, let's just say that we have located this point, and we know that this is exactly this point. Okay, I will need to draw some other stuff, so I need to erase this. Okay, now, so let's just say that we know that this point is the height. But let's just say that now we've introduced a constraint in a general form. So we do not know exactly how this function looks like, right? But for now, let's assume that it's not linear. We will go back to linear case a little bit later. Okay, so what can happen with the constraint? Look, let's just say that it turns out that if I'm drawing this constraint over here, I'm getting a shape like this. And this constraint, this line, look, is given only for x and y, right? So we do not have z anywhere here. C is a constant. So it means that some combination of x and y must be equal to this constant. And look, what has happened over here? Now it means that we are not allowed to choose any value of x and y, but only those who lie on this line. So look, what has changed over here? Look, now, right away we know that this maximum that we found before is impossible to attain for us. So look, what we need to do in this circumstance is to refocus our attention, not to care about every possible point over here, but only on those points that are over here, and we need to choose a point. That is the highest on the yellow line. Okay, so now look. Remember, we are looking at this from above. So z-axis is over here, right? Let's now move to 3 dimensions with this case. Okay, so if we have 3 dimensions, how will it look? Now, of course, we need to draw a sphere. So it's gonna look like, let's just say that our sphere is gonna look like this. And I hope I'm gonna be able to get it the first time. I think I did. Yeah. Okay, so look, now what do we see? Look, we see that this point on the top over here of this sphere is the same top that we see over here. But look, of course, if there would be no constraint, that would be our goal, to get on this point. But look, what else do I see here? Like, if I would draw a line going from this point, I would get some coordinate, let's just say y0 and x0. And look, the problem is that this coordinate, the coordination of this point, so this x0 and this y0, is not on this line. So again, we see that we cannot have this point as our maximum. Look, our choice of option for the best solution has been limited. Now, how has it been limited? Look, now we remember this is part of the sphere we see, this is part of the sphere we don't see. So look, this line, actually, we see it, then it goes below the sphere, right? And then again we see it. So look, what is permitted for us to choose now are only those values of z that are above this line, and they are on a sphere. So look, of course I'm not an artist, and also I'm not a computer, so I'm not sure I'm going to get the right shape that I actually want, but what we would get would look more or less like this. It would be a little bit more shapy, in a way, a bit more curvy than what I draw, but I hope you're seeing where I'm going with this. Look, actually, what this constraint did to us is that it eliminated every other possible value of z from here, right? And we accepted only those values of z that are, you know, given for the coordinates that lie on this line. So look, actually what we have is like we cut out of this sphere the very, very tiny thin slice, you know, and look, out of it we got something that looks more or less like a parabolic shape. And look, so what do we need to do right now? Our goal is to find the top of this thin slice. How will we do it? Actually, we can do it exactly the same way as we did it in case of unconstrained optimization. So we would find a line, a slope that is parallel to the x-axis, and the one that is parallel, point at which also derivative is parallel to y-axis. So we calculate derivative with partial derivative with respect to x and with respect to y. And if we find this top, this location is going to be our maximum. Okay, so how could we do it? Look, as it turns out, there is a very, very simple trick to achieving this goal. Okay, and let me illustrate. First, we're going to build Lagrange function. Okay, so what am I going to do? I'm going to replace z, lowercase z, with big Z. So uppercase Z, capital Z. Okay, and what do I want to have in this Lagrange function? First of all, look, we still want to find maximum of this function, so definitely this function should go inside. And now the second thing, I want to, of course, maintain the fact that this is the function we are actually dealing with. So I don't want to change this function at all. So what can I do over here to do something with it, but actually not do anything to it, is that I can add 0. Right? And look, makes perfect sense. Now, we've got exactly the same function, right? Because fxy and fxy plus 0 are the same thing. But we can go even deeper with this. If I multiply 0 by 3, this is still 0. And actually, I can multiply 0 by any number I want, and I'm still going to have 0 here. So I'm going to multiply it by a number denoted by Greek letter lambda. This lambda denotes something we're going to learn about in the future in more detail, and it's called Lagrange Multiplier. Why is it called Lagrange Multiplier? We're going to learn during Introduction to Economic Analysis. Okay, so look, we haven't changed a thing over here, right? We still have lambda times 0. So, as you probably seen many times in my videos, there is a lot of creative ways in which I can write 0. For example, 2 minus 2 is 0, right? So I can, for example, take 2 minus 2 and put here in place of 0, and it's still going to be true. But of course, 2 minus 2 is not something that would prove very useful over here. So instead of putting something that wouldn't bring us any additional information, why can we put something that will definitely bring some additional information? Okay, and what is this going to be? Of course, we need to utilize our constraint. And look, what do we know from this constraint? We know from this constraint, of course, that some function g, x, y is equal to c. But look, this means that if I'm going to subtract g, x, y from both sides of this equation, I'm going to get that 0 is equal to c minus g, x, y. Okay, and now we've got a 0, but this is a very useful 0, as you will see. Okay, so now I can finally take this 0 and replace it with this 0. And this is a Lagrange function. Look, we actually have the same function because of course we just added 0, but our 0 is now very specific in the sense that those are all the points for which values of g, x, y are equal to c, or all the combinations of x and y for which value of the function g is equal to c. Okay, so now that we've got this, what should we do next? We, of course, need to proceed in exactly the same way as we did previously. So we'll need to start with first order condition. Okay, and what do we do in the first order condition? We take a function and we differentiate it with respect to all the variables in this function, right? Before, we were calculating partial derivatives with respect to x and y, because those were our variables. And they are still our variables over here. But now, we have one more variable. This variable is lambda. Because we do not know what is the value of this lambda, right? So, it would be better if we took this into consideration. And once we actually calculate those derivatives, you will know at this moment you will exactly know why we did this. Okay, so look, first thing we do is the same as before. So we calculate derivatives now of the capital Z, so Lagrange function, with respect to three variables. But let's start with lambda. So I calculate partial derivative of capital Z with respect to lambda. And look, what am I getting? If I'm differentiating with respect to lambda, everything else is constant. So this is gone, and we treat this as a coefficient on lambda, right? before, we equalize it with 0. But look, haven't we seen this somewhere? Look, if I solve this for c, I'm getting that c is equal to g xy. So look, what we get over here is nothing more than a repetition of a constraint that we had over here. So look, now the first derivative with respect to lambda is bringing us only one piece of information. And this piece of information is that all the combinations of x and y's that we take into consideration through function g must be equal to c. Okay, then we calculate partial derivative with respect to x. So, we will get out of this partial derivative of f with respect to x, so fx. And now look, then if I'm differentiating function g with respect to x, I'm going to get partial derivative gx. But we have minus up front of this function and lambda, because c is a constant, so we don't care about it. So we are getting that this is equal to minus lambda gx. And this needs to be equal to 0. Then we differentiate this with respect to y. So we get now fy minus lambda g y equals to 0. And look, out of this, if we would know how does this function look like and this function look like, we would get a system of 3 simultaneous equations with 3 variables, x, y, and lambda, and we could solve this system for all these 3 variables. And now, if we find these 3 variables, of course, we might have more than one triplet, right? We might have a situation in which we have 5 potential candidates for maximum or minimum. But all of them will point us to the point at the top of this parabolic shape. Or of course, remember, the same thing would be for minimum if this sphere would be upside. The spheric shape would be upside down. Okay, now, so this is the first order condition. So we calculate 3 partial derivatives, we set them to be equal to 0, and we solve them with respect to lambda x and y. And look, for now, later on, in Introduction to Economic Analysis, we will be looking for all 3 of those. But for now, just for now, we need to only solve it for x and y. Lambda is inconsequential to us for now. Later on, it's going to be very important. Okay, now, what else we have here? Okay, let me just erase this blackboard. And look, now that we found let's just say that we found a candidate for minimum or maximum. And so how do we decide? Of course, we use second order condition. And we calculate something that is called bordered hashing. Okay, so it's called bordered Hessian because it's like a regular Hessian but with some additional elements. Actually, the name I'm going to explain to you a little bit later. Okay, but how do we calculate it? Look, we calculate it in exactly the same way as regular Hessian. Now we just have more variables. Look, here we have first derivative of partial derivative of big Z, capital Z, with respect to lambda. Here we have first partial derivative with respect to x, and here we have first partial derivative with respect to y. And now look, each of these three derivatives I can differentiate with respect to lambda, with respect to x, and with respect to y. Okay, so over here, now playing, straight to what derivatives will we have where? Here we will have d square z, d lambda square. Here we will have d square z, d x, d lambda. Oh my god, I used the wrong symbol, I used lambda, sorry. And over here we will have d square z, d y, d lambda. Okay, and look, because this is a Hessian, of course, if here we have some element, we will have exactly the same one here. So, of course, if I would differentiate this with respect to lambda, I would get a simply different order over here. But I'm going to write it in a proper order right away. So it's going to be not in a proper order. I'm going to write it in the I will explain in a second. So here we will have d lambda dx. Here we will have d square z dx square. Here we will have d square z dy dx. And now we differentiate this with respect to lambda, so we have d square z d lambda d lambda d y. Here we would have d square z d now we have dx dy, and now we have d square z dy squared. And we remember that this and this are exactly the same expressions. That this and this are exactly the same expressions. And of course this and this are exactly the same expressions. Unfortunately, I prepared the graph, but I think I will have to draw it once again. And a second, because now that we know what we need to have where, we can easily calculate all those expressions. Okay, now if I differentiate the first derivative with respect to lambda, we see that there's no lambda over there, right? So this is going to be 0. Now, if I'm going to differentiate the first derivative with respect to lambda with respect to x, I'm going to get negative gx. And with respect to y, I'm going to get negative gy. Now look, now that I know that negative gx is over here, I know that negative gx is going to be over here. Negative gy is over here. I know that negative gy is going to be over here. Now, so what do I need to do now? Now, differentiate the first derivative with respect to x. With respect to x, so out of that, I'm getting that this is fxx minus lambda gxx. If I'm going to differentiate this with respect to y, I'm going to get fyx minus lambda gyx. But if I have this over here, I need to have the same thing over here. So I have fxx minus fyx minus gyx. And finally, I differentiate this with respect to y, so I'm getting fyy minus lambda gyy. Okay, now look, there is one more trick we can do over here. This is a determinant. And remember, there's one trick with the determinant that I can take any number from any row or any column and put it up front, right? And what I can do over here, look, what I can do over here is that I can take -1 out of the first row, -1 out of the first column. So up front I'm going to have 1, so nothing changes. So I can get rid out of these minuses, and now everything looks nicer. Okay, so what is the condition for maximum and minimum if border Hessian is higher than 0? This is the maximum. If it's lower than 0, this is a minimum. And that's it. In this case, we just need to calculate one Hessian, border Hessian. We do not calculate first principle minors. So this is it. As you see, this case, actually in this case, especially second order condition is easier. Okay, so look, now that we know how it works in general, let's get to the case that we usually have. Because in most economic applications, we're going to use a little simpler version of a constraint. A little simpler version of a constraint. So what if we have linear constraint? Okay, what do I mean by the fact that we have linear constraint? Imagine that constraint is in the form ax plus by equals to c. Look, this is a linear function. Look, I know it doesn't look like this first time you see it, but look, I can solve it for y, and I'm getting that y is equal to -a over b plus c over b, right? If I solve this for y. So this is a straight line, right? This is of course, x. This is a straight line. A linear function. So this is actually a special case of what we had before. So this is definitely going to be an easier example to deal with. Okay, how will it look? First, if we look from the perspective, if we look on the from above on the three-dimensional space, so here we would have x, here we would have y, and let's just say that this is our maximum. This is the top. Well, this is our maximum. This is the spherical shape in which we should look for the maximum. And look, if this is the function we've got, then this function will look, for example, like this. And look, now our focus again should be not to find the highest point on this function everywhere, but only on the yellow part of the constraint. Okay. So, now knowing this, how will it look in 3 dimensions? Well, it will actually look very similar to our previous case. It's of course going to be simpler, because now we've got y. Here we've got some function y plus b x equals to c, and over here we've got the spheric shape, and we know the top is over here, but for us the important part is only the part above the straight line. And we would look for it in exactly the same way. Sorry, that's definitely not look parallel to x-axis. Okay, so we've got tx over here, ty over here. Okay, so now that we know what we are looking for, how do we look for it? Look, again, we need to go through the same steps. Now everything's just going to be simpler. Because first, we need to build Lagrange function. So we're also going to start with fxy plus lambda, and we are adding 0 from this function, right? So, but our 0 is going to be c minus ax minus by. So, over here, I'm getting c minus ax minus b. Okay, and now we go to first order condition. Okay, I'm going to do it over here. Okay, so first order condition. So I differentiate capital Z with respect to lambda. I'm getting that this is c minus ax minus by. I equalize it with 0. And again, look, I just get a repetition of the constraint, which simply tells us that we are looking only for the points above this line. Of course, if we look for maximum, above or below this line, to be exact. But in this particular case, just above. Okay, then I did calculate derivative with respect to x. And what am I getting? Look, out of this, I'm getting fx minus lambda a, right? Because out of this, I'm getting minus a times lambda equal to 0. Then over here, I'm getting fy minus lambda b equals to 0. And look, again, I have a system of 3 simultaneous equations with 3 unknowns, so I can solve them for lambda, x, and y. But of course, for us, lambda is unnecessary, so we are using this system to find lambda and x and y. Okay, so now that we've got this done, we can move on to second order condition. Okay, and look, in second order condition, we just calculate border Hessian. Look, again, nothing happens now, everything's going to be just simpler. here we're going to have dz d lambda, dz dx, dz dy, and we differentiate with respect to lambda, with respect to x, and with respect to y. Okay, and now, because it's super easy, I'm going to do it right away. So look, if I differentiate this with respect to lambda, I'm getting 0. If I'm differentiating this with respect to x, I'm getting negative a, and with respect to y, negative b. If I have negative a and negative b over here, I will have negative a and negative b over here. And look, now, if I differentiate this with respect to x, I'm getting fxx. With respect to y, I'm getting fyx. If I have fyx over here, I will have fyx over here. And finally, over here, fyy. Again, because this is a determinant, I can take negative 1 out of this row and negative 1 out of this column, and as a result, I'm getting this. And look, this is the expression for the bordered Hessian when we have a linear constraint. And look, again, here nothing changes. If this is bigger than 0, we've got maximum. If this is lower than 0, we've got minimum. Now, let me just tell you why is it called bordered Hessian. Because look, if I'm going to do something like this, what is this? Look, this is a regular Hessian for z equals fxy, right? And on the top, it has this additional border, and because it has this additional border, we call it bordered Hessian. Okay, so now we know everything, almost everything, because we haven't actually derived this. But again, it would require from us usage of quadratic forms that we don't have time to do. But again, I'm going to leave a description where in your book you can find a proper and easy, I would say maybe not easy, but accessible explanation of how we get to this bordered Hessian. Okay, so this is it about the principles of finding maximum or minimum of the three-dimensional function under constraint, general and linear. In the next video, I'm going to show you examples of how to solve exercises using what we've just learned. Thank you for your attention.